roller coaster. Start at the top, just creeping over the edge, and a moment later you're found at the top of a loop. The question is, how fast is the roller coaster going around? So the question is, how fast is it going at this point? Energy problem. Here, it was just starting over the edge, so the kinetic energy up here was 0. There's certainly a gravitational potential energy, mgh, however high that is, or mgy. So I think you know this height, you know the weight. I forget what the symbols are. I like y. You know its height in the gravitational field, you know its mass. You can figure out how much energy it has up here. Conservation of energy says the total energy doesn't change. So the energy at all of these different points will have different forms. And remember, the total energy is equal to the different forms of energy. How fast it's going is going to be represented by the kinetic energy, and how much energy is stored in, how much potential energy it has just by virtue of its height in the gravitational field. There's no springs here, there's no change of chemicals, none of the other categories. We're going to assume no friction, so there's no heat loss. These are the only two energy categories. Add them up, and in all the different positions, the energy is not changing. It's going to swap back and forth between these two categories of energy, but the total is not going to change. This is conservation of energy. Conservation of energy. So the kinetic energy is 1/2 mv squared anywhere. So you can tell up top when it's at 0, nothing's happening. And the potential energy due to gravity, mgy, as we've said, those two categories are going to change, but the total isn't. So if we know what the total is here, it's all in gravity, none in kinetic, and it falls a certain distance, we know what its height is here, then we can tell how much it falls, so how much it loses in its energy of gravity is going to be how much it gains in its kinetic energy. So the difference in the energy it has in gravity, the loss of the energy in gravity, that's going to be the difference of heights. That's going to be this loss from up here falling down to there. Is going to be its gain in velocity. So you can equate, you can figure out how much energy is held in gravity here, figure out how much energy is held in gravity here by virtue of the two different heights, and then the difference is going to be the energy picked up by the motion. So you can figure out the velocity. Now, how hard does it press against? How hard does it press against the track at point B? This is a force question. Now we're not using energy. Energy has given us a velocity. And we are now into dynamics and circular motion. We're assuming this is a circle. Anything moving in a circle is necessarily accelerating. Has an acceleration towards the middle, described by v squared over r. Anytime you're accelerating, that's caused by a mass. That's caused by a force. F equals ma. Here, there's a special form for ma. It's mv squared over r in a circle. And we have to ask ourselves, what are the forces on this? There's weight pulling down. I won't have to put it back to there, the arrow's already there. So there's weight pulling down, and there's a normal force pushing down on it. And how much, the actual question is, how hard does it press against the track. It's going to press against the track as hard as the track presses against it. So if we can figure out N, that's how hard. Basically, when two surfaces come together, one is always pushing equal and opposite of the other. So if we can figure out how hard the track is pushing on the roller coaster, that will be equal and opposite to how hard the roller coaster is pushing on the track. The track is pushing on the roller coaster, which is the whole reason it remains in circular motion. Otherwise, it would fly off in a straight line, because that's the direction it's traveling at the top. All right. Total force is equal to, well, there is a net force. It is accelerating, we know that. And the total force is equal to, add up all the forces, that's the weight plus point of contact. Forces are pushes and pulls. Well, the only thing pushing on the roller coaster is the track. So we have, if we lay down a coordinate system, there's y, that's plus. So N is pointed down. Weight is pointed down. And I think in order for it not to be confused by the signs, we have to recognize that this centripetal acceleration is always towards the center. Towards the center. So in this situation, this acceleration is also pointing down, and I'm going to put a negative sign, because the net force is downwards, because the acceleration is downwards here. So there's actually negative signs everywhere, straight across. All things are in. So what we really have is negative m v squared over r. We know r, no m, no v squared from the original. We know negative n, the weight is mg. We know all of these things, we can solve for n. This is a typical example of how we're mixing energy ideas. The energy might give us different positions, it might give us velocities. We can take that, couple it to a circular motion equation here, because it is in circular motion, and then couple that to a dynamics or a force equation. There's three different ideas that we've bridged in one example. Beginning to end energy, circular motion, and then we need to be able to draw a decent force diagram in order to come up with an equation for the net force, which is an accounting of all of the forces.